Hey, so good day. So in last meeting, last video, we talked about torque and we also talked about net torque, which is the sum of all the torques in acting on an ob rigid object. So we mentioned that if the torque or the net torque acting on an object is not zero, then that object will have an angular acceleration. So let's investigate that further. What happens to a rigid object under a net torque? Well, we said that there will be an angular acceleration. That object will have an angular acceleration. But to be very specific, what formula can be used to calculate exactly what the value of that angular acceleration is? So in order to do that, we have to start with a very simple model of a particle of mass m, as you can see here in the drawing. And this particle mass m, there are essentially, if you break down the net force into two components acting on the mass, so maybe the net force acting on the mass has a tangential component of the force, and the net force of the mass also has a radial component of the force. So the summation of Fr, the radial component of the force, that's the component of the force that makes the mass constantly change direction and move in a circle. Whereas the tangential component of the force acting on the mass, or summation of F sub t, um, that is the force that produces the torque that allows the mass to accelerate. So, so for example, if that tangential force does not exist, so if sigma or summation of F sub t is zero, and that the only component of the force is the radial component, then the mass will not have an angular acceleration. But suppose that there is a tangential force component, that force Ft, that's the one that will produce the torque, which will cause the mass to have an angular acceleration. So let's investigate this model further. So we start with Newton's second law, the summation of all forces, all tangential forces is equal to the mass times the tangential acceleration. I want to remind you of a lesson we had last meeting, that tangential acceleration is related to angular acceleration, r alpha. So we will be using this in our derivations. Okay. And we will also use the torque formula, summation of force ER. Okay. So this is just force times radial, the distance from the axis of rotation. This is a formula for torque. And now we substitute sigma ft equals ma2 in here. And then we make some more simplifications. Here we substituted r alpha for 8 sub t. And what we get is this one, no? Summation of torques is equal to mr squared times alpha. So we now have alpha, the angular acceleration, as it relates to torque. And we have this other expression, mr squared, in parentheses. This is something new and this must be relevant. So we give it a symbol I. So basically, the sum of all torques is directly proportional to the angular acceleration of the rigid body, or in this case, the mass. So the stronger the torque, the more the angular acceleration, and it's related by this constant I. So what is this I? there is a name for this I. It's called the moment of inertia, or the rotational inertia. And if you look closely at Newton's second law, no, there are some analogies. So instead of summation of forces, we have summation of torques. Instead of mass, we have I, the moment of inertia. Instead of linear acceleration, we have angular acceleration. So this one is also known as the Newton's second law for angular or rotational motion. Okay, so this is the analog, or this formula that I encircled, summation of torque equals I alpha. This is the rotational analog for Newton's second law. But we have to learn more about I, no? What is this I? Apparently, the formula for I is mr squared, but this is only true for one small particle, right? Rotating about the radius r. And you will soon find out later that the formula for I will depend on what object is rotating, the shape of the object. So, like if you have multiple particles, like if you have a rigid object, you can think of the rigid object as composed of multiple tiny masses. And then what you do then is to get the torques for each individual mass. Get the mass here, get the torque here, get the mass here, get the torque there. And you will get, for each individual mass, you get MI/RI squared. So this is each individual mass has its own rotational inertia, or the tendency of that object or that mass to resist any changes in rotational motion. And you just sum all of them. Then you have here you have a general formula for the rotational inertia of any rigid object, and you just add the mr squareds for each tiny mass in this rigid object. Then you will get the fixed about a certain axis, you will get the rotational inertia for that object. Although I guess you can imagine this is a very cumbersome, very difficult thing to do if you get all of these tiny masses, you get all of the individual masses and all of their distances from the axis of rotation for each tiny mass. And often there are hundreds of thousands, if not infinite number of tiny masses in a rigid object. So this is just a formula, a principled formula, but very impractical to use. And so therefore, we actually have somebody already solved for what the actual formula is for certain shapes, certain idealized shapes, depending on the problem. For example, if we have a problem of a hoop or a cylindrical shell, we already have a formula for that. Don't worry, you will not memorize this. And this is for when the rotation is about the center, right? mr squared, where r is the radius of the cylindrical shell. More interesting, how about the solid cylinder? If the problem is a solid cylinder that is rotating, the formula for I that we will use is 1/2 mr squared. We have, how about this? Now, rotating is a long, thin rod rotating through the center. You have 1/12 ml squared, where L is the length of the rod and M is the mass of the rod. So there are various different formulas for I. How about for solid sphere, right? Rotating about the center of mass, 250 mr squared. But the fact remains, this is the general formula for knowing the angular acceleration. You can just sorry. Oh, that's recorded. Just manipulate the equation, right? So this is the formula for when I ask you to solve for the angular acceleration. And I here in the denominator depends on what kind of object is rotating, what the shape is. Okay, let's see. Let's look at this problem. Okay. A uniform rod of length L and mass M is attached to at one end to a frictionless pivot and is free to rotate about the pivot in the vertical plane as in the figure. The rod is released from rest in the horizontal position. What are the initial angular acceleration of the rod and the initial translational acceleration of its right end? So here it can be seen that it is the force of gravity that will produce the torque that will cause the object to have an angular acceleration. And whenever we assume that this rod is, the mass of this rod is evenly distributed throughout its body. And so therefore, if that happens, we can think of the gravitational force as acting on the center of the mass, center of mass of the object in the middle, right? Of course, the force of gravity um it like it is everywhere along the rod, but for simplification purposes, we can think of the force of gravity as only acting at the center of the object. And of course, the formula is just the weight mass of the rod times G 9.8 meters per second squared. So this, again, this force of gravity, this is the one that produces the torque which causes the rod to accelerate. So, all right. So, what is this? So, there's only one force producing torque, and that's the force of gravity. And if you remember formula, it's RF, torque is RF sine theta, sine phi, or it's FD. Remember, D here is the moment arm, but there's another formula. This is F perpendicular R. So, what is this formula? Um, F perpendicular is the component of the force that is perpendicular to R. So, if F is not perpendicular to R, then you have to calculate what F perpendicular is. But in this case, so this is your R, right? R is, remember, R starts at the pivot, the axis of rotation, to the point of application of the force. And R happens to be half of L, so L over 2. That's where L over 2 comes from. And now, this is your force that is producing the torque. And as you can see, this force is already perpendicular to R. So, this formula stands F perpendicular to R and R. So, F perpendicular is mg and R is L over 2. Yun. And remember that alpha is summation of torques over I, and in this case, 1/3 ml squared, you have to refer to this slide. There it is. It's not here actually. Here it is. Long thin rod with rotation axis through one end. This is exactly what our problem is, and this is where the formula for I comes from, 1/3 ml squared. That's what they substituted here, 1/3 ml squared. Simplification will give us 3g over 2n. for the angular acceleration of this rod. And the translational acceleration, which is also asked in the problem, is just equal to r alpha, right? And our r here is the whole length of the rod, which is L, because the question is, what is the initial translational acceleration at the right end? So right here, what is the translational acceleration here? And that is our R for that part of the problem, which is equal to the length of the rod. So that's what this is. So that's why we have L times alpha. Okay. I have to end here, but I hope to give more examples in the future. So thank you. And I have somewhere to go to. That's why I have to end this abrupt.